Hello everyone, welcome back to our channel gsipucmysuru. This is the 17th session of the second chapter, that is Principles of Electricity, Network Theorem and AC Principles. In the last few sessions, we solved some of the problems on superposition theorem and KCL and KVL, and also we solved a single problem on Thevenin's theorem. In this session, we will be solving some more problems on Thevenin's theorem, and then we will move on to the next topic, that is the maximum power transfer theorem. So, let us look into the first problem of this session. The problem is, you have to find the Thevenin's equivalent circuit for the given circuit diagram. Here they have given one circuit diagram which contains 3 resistors R1, R2 and R3 and one voltage source, that is having a voltage of 5 volts, and these two terminals are named as A and B, and that is called as the voltage across those two terminals are called as VThevenin. You have to find out the Thevenin's equivalent circuit. Thevenin's equivalent circuit is nothing but a circuit which contains only one voltage source which is named as VThevenin, and to that voltage source will be connecting one single resistor which is named as RThevenin. So, let us first find out the VThevenin voltage for this particular circuit. So, VThevenin is equal to the voltage source V into the resistance across which I am measuring the voltage. VThevenin is same as nothing but the voltage across this resistor R2. So, the total voltage into this resistance divided by the sum of these two resistance. So, the total voltage into R2 divided by R1 plus R2. So, the total voltage is equal to 5 and the resistance value of R2 is equal to 1 divided by R1 value is also equal to 1 kilo. Let me write it as 1 into 10 to the power of 3. 1 plus 1 into 10 to the power of 3. Because both the values R1 and R2 are 1 kilo, and I am taking that kilo as a common factor. So, within the bracket I am writing it as 1 plus 1. So, 5 into 1 10 to the power of 3, 10 to the power of 3 gets cancelled. So, 5 into 1 is 5 divided by 1 plus 1 is equal to 2. So, I will be getting the VThevenin voltage as 2.5 volts. Now, you have to find out RThevenin, for which we will be shorting this voltage source. So, I will be getting the diagram like this. So, the resistance across these two terminals A and B is nothing but RThevenin. Here it is 0.5 kilo, 1 kilo, and even this is 1 kilo. It is named as R1, R2 and R3. You have to find the RThevenin across these two terminals A and B. So, you have to look from this point. R1 and R2 are connected in parallel, and that parallel combination is connected in series with R3. So, RThevenin is equal to R1 parallel to R2, and that parallel combination is in series with the third resistor which is named as R3. Now, R1 parallel to R2, we are having a direct formula, R1 R2 divided by R1 plus R2. So, let me substitute those values. 1 kilo into 1 kilo divided by 1 kilo plus 1 kilo, that is 1 plus 1 kilo, plus R3 value is 0.5 kilo. So, this kilo gets cancelled with one of the kilos. So, 1 into 10 to the power of 3 divided by 2 plus 0.5 into 10 to the power of 3. 1 divided by 2 into 10 to the power of 3 is 0.5 into 10 to the power of 3 plus 0.5 into 10 to the power of 3. So, 0.5 plus 0.5 gives me 1 into 10 to the power of 3 ohms. So, this is the RThevenin for this given circuit. So, the equivalent Thevenin's equivalent circuit is like this. This is the VThevenin whose value is equal to 2.5 volts. For that VThevenin, we will be having a resistance which is connected in series, and that resistance will be named as RThevenin, whose value is equal to 1 kilo ohms. So, this is the equivalent circuit, Thevenin's equivalent circuit for this particular circuit diagram, where VThevenin is 2.5 volts and RThevenin is 1 kilo ohms. Clear? Now, we will move on to the next problem. So, this is the second problem. Using Thevenin's theorem, find the current through 20 ohm resistor of the circuit. Here they have given a circuit where 4 resistance values are given, 4 resistors are connected, 4 ohms, 2 ohms, 6 ohms and 20 ohms, and only one voltage source whose value is equal to 24 volts is given. You have to find out the current through this 20 ohm resistor. So in this particular case, we have to consider this 20 ohm itself as a resistor. So the very first step what we are going to do in solving this Thevenin's theorem problems is, we are going to identify the load resistor and remove that load resistor. After removing that load resistor, we are going to name the voltage across that terminals as Thevenin. So let us write that particular diagram where 20 volts will be removed and the voltage across that terminals will be named as Thevenin. This is 4 ohm, 2 ohm and this is 6 ohms, whereas this is 24 volts. Now, if you are going to consider this particular loop, this loop contains one voltage source and one 4 ohm resistor as well as one open terminals. So, that 24 volts will be divided into the voltage drop across this 4 ohms as well as the voltage drop across these two terminals, which is named as Thevenin. So that 24 volts is equal to the voltage drop across 4 ohm resistor, let me name it as V4 ohm, plus Thevenin. I don't know Thevenin, that is what we have to find out, and we don't know the voltage across 4 ohms also. So what can be done over here? Since this is an open terminal or since this is an open circuit, the current cannot flow over here. So the current which is generated or the current which is produced from the 24 volts has to flow in this particular direction, and that same current will flow through 4 ohm, 2 ohm as well as 6 ohms, and that will complete its path in this particular direction, right. So what we have to do is, let us first find out the current for this. So the current I is equal to, that is the total current. The total current I is equal to V divided by R total, where V value is equal to 24, R total value is 4 plus 2 plus 6, because all of these 3 resistors are connected in series. So 24 divided by 12 gives me 12 ones are 12 twos are, so the total current I is equal to 2 amps. So the current I which is flowing in this particular circuit is 2 amps. Now, the voltage across 4 ohm is equal to the current flowing through that resistor into that resistance value plus Thevenin. This is 24. This is the resistance that is 4 ohm resistor. Let us name these resistors as R1, R2, R3. So, this is equal to I into R1. So, 24 is equal to 2 into 4 plus Thevenin. So, Thevenin is equal to 24 minus 4 2s are 8. So, Thevenin value is now equal to 16 volts. Clear? So, 24 minus 8 gives me 16 volts. Now, we have to find out Thevenin. To find out Thevenin, what we are going to do? We are going to remove this voltage source. We are going to short this voltage source, and the circuit diagram will be like this. And these the resistance what we are going to measure between these two terminals is named as Thevenin. This is equal to 4 ohm, this is 2 ohm and this is equal to 6 ohm. Now if you look at this particular diagram, this Thevenin is present between these two ends. 6 and 2 ohms are connected in series, whereas this 4 ohm is connected in parallel combination with these two resistors. So Thevenin, the diagram will be like this. The simplest diagram will be like this. One is 4 ohm and the other one is 6 plus 2, which is equal to 8 ohm, and this is equal to 4 ohm. So Thevenin is equal to 6 plus 2, and this is in parallel combination with 4 ohms. So 6 plus 2 is equal to 8. 8 is in parallel combination with 4 ohm. So Thevenin is equal to 8 into 4 divided by 8 plus 4. 8 4s are 32 divided by 8 plus 4 is equal to 12. So 32 divided by 12 gives me 2.66 ohms. Clear? So our Thevenin is equal to 2.66 ohms. Now let us draw the Thevenin's equivalent circuit by rubbing this particular diagram. Thevenin's equivalent circuit contains VThevenin in series with RThevenin, and across this we are going to connect the load resistor, that is nothing but 20 ohm in this particular case. VThevenin is 16 volts, RThevenin is 2.66 ohm. Now you have to find out the current flowing through this. Let us name it as IL. So now IL is equal to VThevenin divided by RThevenin plus RL, where RL is nothing but 20 ohms. So VThevenin is 16 divided by RThevenin is 2.66 plus RL value is equal to 20. So 16 divided by 22.66. So IL is equal to 0.716 amps. So IL for this particular problem is 0.716 amps. That is what we have to find out in this particular problem. Find the current through 20 ohm resistor. This is the next problem. Using Thevenin's theorem, find VL and IL for the given circuit. Here they have not mentioned which is RL. If they are going to mention any of the resistor as RL, then we can easily remove that RL, and the current flowing through that resistor can be considered as IL, and the voltage which is measured across that RL can be considered as VL. But here they have not even mentioned the load resistor. So we can take, or we can consider this itself as the load resistor. All the values of the resistor what is given in this particular circuit diagram is 8 ohms, and the voltage source which is connected in this problem is 60 volts. So the very first step while solving this Thevenin's theorem is identify the load resistor and remove that load resistor. So the circuit diagram will be like this: 8 ohms, and these two terminals will be named as A and B, and the voltage which is measured across these two terminals is named as VThevenin. So these are 8 ohm resistor. This is equal to 60 volts. Now as usual, VThevenin is equal to 60 into VThevenin is nothing but the voltage across this 8 ohm resistor. So the total voltage into this resistance divided by sum of these two resistance. Since this terminal is open circuited, the current cannot flow over this particular circuit. So you have to consider this loop where 8 ohms are connected in series. 60 into 8 divided by 8 plus 8. So 60 into 8 is 480 divided by 16, and that will be equal to 30 volts. So VThevenin is equal to 30 volts. Now we have to find out RThevenin, for which we are going to short circuit the voltage source, and the circuit diagram will be like this, and the resistance which is measured across these two terminals will be named as RThevenin, and these are 8 ohms. If you look from this side, these two resistors whose values are 8 ohms is connected in parallel, and this parallel combination is connected in series with this 8 ohm. So RThevenin is equal to 8 parallel to 8, which is in series with 8 again. So 8 into 8 divided by 8 plus 8 plus 8. 8 8s are 64, this is 8, divided by 16 plus 8. 16 ones are, 16 fours are. So RThevenin is equal to 8 plus 4, which gives me 12 ohms. Now let us write the Thevenin's equivalent circuit, where we will be having a voltage source which is named as VThevenin, that will be connected in series with RThevenin, whose value is equal to 12 ohms, and we will be having a load resistor whose value is equal to 8 ohms. This VThevenin value is equal to 30 volts. Now we have to find out VL as well as IL. So the current which is flowing through this resistor is IL and the voltage which is measured across this load resistor is VL. So IL is equal to VThevenin divided by RThevenin plus RL, where VThevenin value is 30, RThevenin value is 12 and RL value is equal to 8. So 30 divided by 12 plus 8 gives me 20. So the answer is IL value is 1.5 amps. With this current IL, we have to find out VL, where VL is equal to the current flowing through that resistor IL into that resistance value RL. So 1.5 into 8 gives me 1.5 into 8, VL is equal to 12 volts. So the current which is flowing through this resistor is 1.5 amps, whereas the voltage across that 8 ohm resistor is equal to 12 volts. These are some of the problems on the Thevenin's theorem. Now we'll move on to the next topic of the same chapter, that is maximum power transfer theorem. The maximum power transfer theorem states that the maximum power will be transferred from the source to the load when the load resistance is equal to the Thevenin's resistance. We are having a circuit, a complex circuit. Let us consider that we are having a complex circuit which will be having a source and a load resistance will be given. And according to this maximum power transfer theorem, the power transferred from the source to the load will be maximum when the load resistance value will be equal to the Thevenin's resistance. So the same circuit can be written as, this is a voltage source which is in series with RThevenin, then we will be having a load resistor here, this is VThevenin. So for calculating the power, we are having three different formulas, where P is equal to V into I, P is equal to I square into R, P is equal to V square divided by R. Let us use this particular formula, P is equal to I square into R. So the power delivered to the load will be equal to IL square into RL. The current which is flowing through that load resistance will be named as IL and that load resistance will be named as RL. But from the Thevenin's equivalent circuit, IL can be calculated using the formula VThevenin divided by RThevenin plus RL. So let us substitute here, IL is equal to VThevenin divided by RThevenin plus RL whole square into RL. So this is equal to PL. But according to this maximum power transfer theorem, RL must be equal to RThevenin, only then the power which is transferred from the source to the load will be maximum. So let us substitute RThevenin value as RL itself. So PL is equal to VThevenin divided by RL plus RL whole square into RL. So VThevenin divided by 2RL whole square into RL. Let us remove this bracket. VThevenin square divided by 2RL whole square is equal to 4RL square. 4RL square into RL. This RL gets cancelled with one of the RL which is present in the denominator. So PL is equal to VThevenin square divided by 4RL. But the power transferred will be maximum when the load resistance is equal to the Thevenin's resistance. So RL can be replaced by RThevenin. So the maximum power PL max will be equal to VThevenin square plus 4RThevenin. VThevenin square divided by 4RThevenin. So this is the power relation using which you can calculate the maximum power which will be transferred from the source to the load. So while plotting a graph of RL versus PL, that is the load power and the load resistance, the power curve will keep on increasing with increasing value of RL. But after some point it starts decreasing, and the point at which the maximum power is reached, that is nothing but R Thevenin, and that maximum power itself will be named as the PL maximum. So, the power delivered from the source to the load will be maximum when the load resistance value will be equal to Thevenin's resistance of the given circuit. Now, let us try to illustrate this with one simple problem. So, this is the problem what they have given. Consider the network shown in figure. Given RPS in volts is equal to, let us represent that in the diagram itself. So, RPS value is equal to 5 volts. R1 value is 1 kilo ohm. R2 value is also equal to 1 kilo, and R3 value is equal to 100 ohms. Calculate the power delivered to RL. So, you have to find out the power delivered to the load resistor what they have given, that is RL. So, let us first find out R Thevenin, for which you have to remove this load resistance RL and short the voltage source, that is 5 volts. R1, this is R3, and here we are having a current source. This is another load whose value is equal to 1K, and this is equal to 100. These are the 2 points across which you have to measure what is called as R Thevenin. This 1 kilo and 1 kilo is in parallel, and that parallel combination is in series with 100 ohm. So, R Thevenin is equal to 1 kilo parallel to 1 kilo, which is in series with 100 ohms. So, 1 kilo in the sense 1 into 10 to the power of 3 into 1 into 10 to the power of 3 divided by 1 plus 1 into 10 to the power of 3 plus 100. 10 power 3 gets cancelled. So, 1 into 10 to the power of 3 divided by 2 plus 100. So, 1 divided by 2 into 10 to the power of 3 gives me 0.5 into 10 to the power of 3 plus 100. So, you have to convert this kilo, that is 10 to the power of 3 into these kind. So, this is equal to 500. Shift the points to the right to 3 places, 1, 2, 3. So, 500 plus 100. So, R Thevenin is equal to 600 ohms. So, you have found out R Thevenin value. So, calculate the power delivered to the load, that is nothing but PL equals IL square into RL, where RL is nothing but R Thevenin itself. So, IL square calculate madake, that is we are going to use V Thevenin divided by R Thevenin plus RL anta. But here in this problem they have mentioned IL value as 2 milliamps directly. So, let us use that value 2 milli in the sense 2 into 10 to the power of minus 3 whole square into RL value is 600. So, here RL value is not mentioned. You have to find out RL value by finding this R Thevenin value, which is same as that of the load resistance. So, 2 into 10 to the power of minus 3 whole square gives me 4 into 10 to the power of minus 6 into 600. So, 6 4s are 24 into 24 00 into 10 to the power of minus 6. So, this is equal to PL. So, PL is equal to 24,000 microwatts. 10 to the power of minus 6 is micro. But if you want to keep this in milliwatts, 2400.0 anta ide. So, if you are going to shift the point towards the left side, so it will become 2.4 into 10 to the power of minus 3 watts or 2.4 milliwatts. So, the power delivered to the load when R Thevenin value or the load resistance value is equal to 600 is 2.4 milliwatts. This itself is the maximum power which will be transferred to the load resistance where the 5 volt voltage source is connected. Clear? So, in today's session we will solve some of the problems on Thevenin's theorem, and we learned the statement of the maximum power transfer theorem. In the next session, I will be coming with few more problems on the maximum power transfer theorem, and we will move on to the next topic of the same chapter. Until then, take care. Bye-bye.